Welcome to Learning to Engineer. In this video, we are going to measure the value of unknown resistance by using bridges. In this video, we would have followed a procedure to measure the resistance by using Wheatstone's bridge. We are going to do the similar process. We are going to arrange the arms of the bridge, which has one arm of unknown resistance and the other arm of adjustable standard resistance. We are going to get the bridge be in balance position, just like how we did in Wheatstone's bridge. By adjusting the value of resistance and the inductance, we are trying to balance the bridge and then find out the value of unknown inductance. Let's get started. This is called as Maxwell's Inductance bridge. It has one arm of unknown resistance. This is the unknown resistance. Let me mark it as Rx. This is the unknown inductance Lx. Let me mark this to be R2 and this to be L2, but it also contains a small resistance small r. Both of them are variable. This resistance is R3 and this is R4. R3 and R4 are standard known resistances. You have a detector connected between these two terminals and you have a battery connected to this terminal. We are going to measure the unknown resistance by this bridge. The unknown resistance and unknown inductance will be placed in the first arm. In the second arm, we have a known and adjustable resistance. Also, we have a known and adjustable inductance over here. Then we have this resistance R3 and R4, which are in these two arms. They are standard resistors used for balancing this bridge. When this bridge is balanced, the potential at this point and the potential at this point will be same, right? So in that case, the current flowing through this will be 0. So in the case where this happens, the current which is flowing into this arm will flow directly into this arm, and the current that flows into this arm will directly flow into this arm. If the battery is supplying a voltage of E, the voltage of E will be applied across these 2 points, and this voltage will be same across this arm as well as this arm. So taking into that consideration, the value of Rx plus J times Lx multiplied by the fourth arm R4 will be same as R3 multiplied by R2 plus small r2 plus J omega L2. For time being, I am having this resistance to be R2 dash. Later on, after doing the entire derivation, I will substitute R2 dash as R2 plus small r2. Okay, so I hope you guys will be able to follow that. So I'm just going to cross multiply inside the brackets and equate the real terms and the imaginary terms. After I equate them, you will be able to find out the unknown resistance as well as the unknown inductance. Oh, this is J omega Lx. I'm sorry, this is J omega Lx. By mistake, I wrote it as JLx. Okay, so this is Rx into R4 plus J omega R4 into Lx, which is equal to R3 into R2 dash plus J omega into R3 into L2. So we have 4 terms over here. This is the real term and this is the imaginary term. We can equate both of them. So by equating real terms, we get Rx multiplied by R4 is equal to R3 into R2 dash. Pretty similar like Wheatstone's bridge. Now we want to find out the value of Rx. Rx will be R3 into R2 dash divided by R4. So this is the value of Rx. We have to now substitute the value of R2 dash as R2 plus capital R2. Let's just hold this and then equate the imaginary terms as well. So by equating imaginary terms, we will be getting R4 into Lx to be same as R3 into L2. So we have to find out the value of Lx. So let's isolate Lx and then we will be getting R3 into L2 divided by R4. So this is the value of the unknown inductance. This bridge is pretty simple. So now by using Maxwell's inductance bridge, we have found out the values of the resistance and the inductance by using this bridge. we have to be varying the value of R2 and L2 in order to find out the bridge balance condition. And after we find out the bridge balance condition, we have to note down this value of R2, small r2 and L2, and then we can find out the values of the inductance and the resistance. Now let's see the Maxwell's inductance capacitance bridge, which has an adjustable arm of capacitance in it. By adjusting the value of capacitance, we are going to find out the unknown inductance. Let's see that method. This is the Maxwell's inductance capacitance bridge. In this bridge also we can find out the value of unknown inductance, but we are going to adjust the value of the capacitor and resistor instead of the inductor. In this bridge, here we have the unknown arm and here we have the variable standard arm, meaning that these arms will be varying the value of resistance in order to get the bridge balance. In any bridge that you take, there will be 4 arms, out of which one will be the unknown arm, one will be the variable arm. Why do we need a variable arm? Only then we can adjust the value of one resistance or one impedance in order to get the bridge balanced. Only when the bridge is balanced, you can apply the formula in order to find out the inductance and the resistance. Otherwise, the bridge will not be balanced, and even though you derive a formula and apply that formula, it will not hold good, because you are doing the derivation under one condition, that the bridge is balanced. So you should first balance the bridge and then find out the value of unknown impedance. So when the bridge is balanced, the potential across these two ends will be same. So there won't be any current that is flowing into this arm. So the current that is flowing into this will directly flow into the current into this third arm. Similarly, the current flowing into the second arm will flow directly into the fourth arm. Let's look at the derivation. So when the bridge is balanced, you will be getting the equations as R1 plus j omega L1 times R4 parallel with capacitive reactance. I am just putting it as Xe here. Later on I will be substituting it as 1 by j omega C4. Okay, so it is just Xe4 right now. Same as R2 into R3. Let me just find out R4 parallel with Xe4 separately. Maybe I'll use a different color for you. R4 parallel with C4 is equal to R4 into 1 divided by j omega C4. I'm sorry, this is Xe4. Okay, so R4 into 1 by j omega C4 divided by R4 plus 1 divided by j omega C4. So the value of R4 parallel to Xe4 will be R4, where here these two terms will be cancelled and you are going to multiply it to this term. So you will be getting the denominator term as j omega into R4 C4 plus 1. So let's substitute this value over here. So on substituting, you will be getting R1 plus j omega L1 into R4 divided by 1 plus j omega R4 C4, which is equal to R2 into R3. The equations becomes easy for us if we cross multiply. There is no imaginary part, so it's even more simple now. Okay, so this implies that R1 into R4 divided by 1 plus j omega R4 C4 plus j omega L1 into R4 divided by 1 plus j omega R4 into C4. This is equal to R2 multiplied by R3. We can just club both of them and write R4 C4 plus j omega into L1 R4 divided by 1 plus j omega into R4 C4. This is equal to R2 multiplied by R3. So we can just cross multiply like this and then separate real terms, imaginary terms. Then it's going to be a child's play for us. So R1 into R4 plus j omega L1 R4 will be R2 R3 multiplied by this term, which is 1 plus j omega into R4 into C4. So R1 R4 plus j omega into L1 R4 is equal to R2 R3 plus j omega R2 into R3 into R4 into C4. Okay, so we have this real term and we have this imaginary term. So on equating real terms, we will be getting R1 is equal to R2 into R3 divided by R4, where R4 is the variable resistance over here. Let's park this aside. Now let's equate the imaginary terms. We will be getting j omega L1 R4 to be same as j omega R2 R3 R4 into C4. So now the j omega terms will be cancelled, R4 terms will be cancelled. So the balance is L1. So L1 is equal to R2 into R3 into C4. Right? Let's park this. Now we have found out the value of unknown resistance as well as unknown impedance. Here in both the values, if you observe, even though we have a AC circuit, it doesn't depend on the term omega. Okay, so whatever be your angular frequency of the source, it doesn't affect this. The source's angular frequency doesn't depend on L1. So this is quite a reliable method, but you can use it only when the Q factor of the coil is up to 10. At higher Q factors, you won't be able to use this. I'll explain you the reason. If you observe the circuit, you have to vary the value of this capacitance and resistance in order to achieve bridge balance. Getting a higher value of resistance, getting a higher value of capacitance, especially a variable capacitance, is not that easy. And you have to be mindful of the capacitance losses also. So it is not a very advisable procedure to use this for higher values of inductance. When the Q factor of the coil is less than 10, only then you can use this setup in order to measure this. If you have the Q factor greater than 10, what should you do? We will see that in our next video. So thanks for watching. Keep practicing problems on this so that you get a good hands-on on this. And if you want me to solve a problem, do let me know in the comment section so that I will be able to solve a problem for you in this topic. Okay, so thanks for watching. In our next video, we will see what will happen when the value of inductance is high, when the value of Q factor is more than 10, how to find out the value of the unknown inductance by using bridges. Okay, we will see that in the next video. So subscribe to my channel for more updates and also ring the notification bell so that you will be notified when I am publishing this video. Thank you.